Hey guys, gonna start the notes on chapter 16. I realize a lot of you may not have printers. I put the filled out version on Google Classroom as well as the version with blanks. If you do have access to a printer, I would encourage you to print these out so you can fill them in. But if you don't, I would again encourage you to get some scratch paper so you can at least kind of jot down some notes as you watch that you can then have to look at when you look at the filled out version on Google Classroom. Alright, so this chapter is all about atoms and starting to think about how do those chemical changes from chapter 15 really work. So scientists used a 1 to 2 letter, what we call a symbol. And usually symbols are like, dollar signs and exclamation points and things are what we think of as symbols. But in chemistry, a symbol is made of letters. And every symbol starts with a capital letter. There we go. And if there are other letters, some of them are just one letter, so there'll be a capital letter. But some of them have symbols that are more than one letter. And after the first letter that is capital, the rest are always lowercase. Okay, this starts to matter when we have compounds that are made of more than one. So if I get a compound made of C is for carbon and O is for oxygen. So they're both capital letters, so I know that that's two different elements. But there's another element that's cobalt. That is C lowercase o. That's one symbol. Okay, so if your handwriting's really bad and you write maybe like something like this, you're like, oh, I don't know. Is that a capital O for oxygen or is that a lowercase o, meaning this whole thing is cobalt? So remember, if the beginning of each element symbol is capital, if there's more than one letter, then it's following letters are lowercase. A lot of symbols start with the letter the element's name starts with, like carbon starts with a C, and oxygen starts with an O, and cobalt starts with a C. But some don't make as much sense as all that. So sodium, you think sodium, okay, so it should be an S, maybe an SO, but that's not it. Okay, sodium symbol is Na. Most of the symbols that are weird, that don't really make sense to us, are based on Latin, or I think there's a couple that are Greek, but most of them are Latin. In sodium is natrium in the Latin. So that's kind of the origin of the symbols that seem like they don't make sense. It's from another language. And the symbols are the same no matter what language you speak. And so there you go. Alright, so subatomic particles. So sub, when you see the prefix sub, just like a submarine, not like the sandwich, but the submarine ship that goes underwater, or a substitute teacher that works under the normal teacher, right? They're beneath, it sounds really mean, but the idea is they're working under that person. Sub means beneath or less. Okay, so subatomic particles are less than or beneath an atom. Okay, so this is going to make more sense when we get down here. But we're talking about atoms. That is the smallest functional particle of matter. If you get smaller than an atom, okay, those particles don't really exist by themselves, right? They only exist when they are part of an atom. So it's made of smaller things, and those are our subatomic or less than atom particles. And you have probably heard of these, but we'll talk about them in a little more detail than you probably have before. So these are the old protons, neutrons, and electrons. Okay. And these are very, 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 very exceptionally tiny. When we try to measure them, we measure their mass in a unit called atomic mass units. The unit we measure the mass of atoms in. Okay? And we don't want to write that out every time, so we use AMU to kind of abbreviate atomic mass units, or the units we measure the mass of atoms in. Most of the mass of an atom is here in the nucleus. And we'll look at a picture on the next page. But it's the tiny, tiny, tiny dense center of an atom. Okay, so of the entire volume of an atom, I was watching a documentary once and it said if the whole atom was like the size of an NFL football stadium, the nucleus would be about the size of a basketball in the middle. Okay, so it's really, really tiny, even much, much, much tinier than the entire volume of the atom. And in the nucleus there are protons and neutrons, so let's learn a little more about those. Okay, protons are positively charged, and they have a mass of 1 AMU. And why not? Okay, this is a made-up unit. We might as well make it exactly the size of 1 proton. Makes things a lot easier when we go to figure out the mass of atoms. The number of protons determines the element an atom is, and we call it the atomic number. Okay, before I even go on any further, in your physical science books, there is in a periodic table, I think it's on the inside cover or the back cover, or you can always find one online. One I like, really easy to find, is just ptable.com, and it's really interactive and useful. Okay, so protons are positively charged, and then we have neutrons are not charged, or we say they are neutral, and also have a mass of 1. Alright, so those are the 2 particles in the nucleus, the protons and the neutrons. So let's move out of the nucleus, where we have what's called the electron cloud. Okay. This is the area outside of the nucleus, and it takes up most of the volume of the atom. Remember, think about the NFL stadium analogy. So if the nucleus is the size of a basketball, the electron cloud takes up the rest of the space of the atom, which would be a whole lot of space in the analogy of an NFL stadium. But they have almost none of the mass. Okay, they're very, very, very tiny, but they take up a lot of space. But why? If they're so tiny, why do they need so much space? And here's the reason of it. Is they are flying around. They're moving insanely fast. Okay, so let's think about this again. So protons were positive, electrons are negative. And they have almost no mass. Like I said, they're very, 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 very tiny, even much, much tinier than the protons and neutrons. Their mass is about 1/2000th the mass of a proton or a neutron. So it would take 2,000 electrons to get to the mass of 1 proton or neutron. So, again, so here's our nucleus with the protons and the neutrons. We have the little plus signs in the protons because they're positive. We put anything in the neutrons because they don't have a charge. And here's the electrons. So what's the rest of this gray space? Okay, there's nothing there. Well, it's still part of the electron cloud because these electrons are moving around like crazy. Okay, so they're really filling up this space with their motion. Okay, just like if you had a fan, like a desk fan or a fan, fan trying to move air around. If the fan was not moving, the blades don't take up all that space, right? But if the fan's running and the blades are moving around really fast, you don't want to try to be like, oh, I'll just stick my hand in the space where there is no fan blade right now. They're there, right? Because they're moving so fast and they're taking up all that space because of their fast motion. Ooh, that pen looked weird like that. Alright, so protons and neutrons are each made of 3 smaller particles called quarks. And for right now, I just want you to know quarks are the even smaller things that protons and neutrons are made out of. Go ahead and take a college physics course if you want to learn much more about quarks. We're just going to leave it right there. So since atoms are so tiny, we need models to try to understand them better. And there was many different models of the atom. And as we learn more, our models get what we believe to be more and more close to reality. So we had John Dalton. And if you watched the Edpuzzle I assigned the other day, then you have already heard of John Dalton. But he proposed what was called the very first atomic theory. It was in the late 1800s, so over 100 years ago. And it had these 5 main ideas that were absolutely groundbreaking at the time. Okay, so he said all matter, okay, solids, liquids, gases, metals, non-metals, everything is made of atoms. Okay, and people are like, well, we can't see them. That's a pretty bold claim for you to say everything is made of something that we can't see, right? He also said atoms are indivisible, which would mean can't be broken. When you say the Pledge of Allegiance and you say indivisible, you're saying that America is not going to be broken. Okay, so atoms of the same element, he said, well, if they're the same element, they are the same size. Okay, and atoms of different element are different sizes. That's an I. And he said atoms of different elements combine in whole number ratios. Okay, so he says, I think that they can combine maybe 1 atom of this red thing and 2 of this black atom. Why not? Okay, he says, I think they could combine like that. Maybe they could combine like this. Okay, so this would be a 1:2 ratio, and this would be a 1:1 ratio. But he says, I don't think it's possible to have one of those and half of one of those. So that would be a 1 to 1.5, and he says, I don't think this happens. They've got to be whole number ratios. And he was absolutely right. Alright, and oh, criminy. This is one of his ideas here, so this should be a part of atomic theory. Okay, so his last idea of atomic theory is people knew about reactions. They knew about burning things and, you know, all kinds of chemical reactions, but they didn't really know what was happening. And he said, I think what's happening is we're taking atoms and we're breaking them apart, not like breaking them like into smaller atoms, but taking the atoms, breaking them apart from each other, and putting them back together in a different way. I like to think of this like Legos. Right, so if I had like 6 Legos put together a certain way, I could take them apart and put them back together a different way. But I'm not taking any individual Lego piece and breaking it. I'm disassembling and reassembling in a different way. I'm not breaking any of the plastic pieces apart. All right, so last little bit in this section here. Dalton's theory was great, but as we learn more, as science gets better, we have to add to it and modify it. So in 1926, right, so we have the electron cloud. Right, he didn't know about the electron cloud yet. And we figured out the electron cloud is very large compared to the nucleus. And I kind of talked about this on that picture. Even though the electrons themselves are the smallest by a lot, remember that it takes 2,000 electrons to come up to the size of 1 proton or 1 neutron. So most of the volume of the electron cloud is empty space, meaning there's nothing there really. Okay, so if I could freeze time like that, and the electrons stopped moving, the electron cloud would be mostly empty. But since they're moving so fast, that space is pretty much taken up consistently. So since electrons move so fast, they need all that space. And I said, so think about a fan. The blades are relatively small, excuse me, but when they're moving, they need all of that space. So since an electron's mass is so tiny and their velocity so great, there's a theory in science that says it is impossible to pinpoint where an electron is at any particular moment, which is why when we call it the electron cloud, that idea kind of works pretty good, because it's just kind of this fuzzy area where the electrons are, but we're not saying, oh, there is an electron and there is an electron. It's kind of like, oh, they're around in that general space. So there's section 16.1. As always, let me know if you have any questions. I'll probably put up some sort of short assessment for this. See you later.